Hey guys, Miss Jenkins here, getting ready to take you into your next virtual lesson. Our next section, section 8-2, special right triangles. So in this section, you are going to learn that certain right triangles have properties that allow you to use some shortcuts to determine the lengths of the sides without using Pythagorean theorem. So last section, we were working with Pythagorean theorem, using the formula, crunching numbers. This section more so deals with some certain triangles that are special, which we do not have to use Pythagorean theorem for. We can, in fact, use a few shortcuts that will help us. Okay, so first up on our list is a right isosceles triangle, which you do have some experience with. Isosceles triangles, right isosceles triangles, where both of your angles are 45-degree angles. Another name for an isosceles right triangle, which you will hear in this section pretty often, is a 45-45-90 triangle. 45-45-90. This is a right isosceles triangle. So if each leg, we'll say, has a length of x and the hypotenuse has a length of y, we're going to solve for y, or we're going to see what the hypotenuse is equal to every single time in these right isosceles triangles, regardless of the lengths of the legs or the hypotenuse. You can pretty much solve for the hypotenuse every time with a special formula. So let me just show you so that this makes a little bit of sense. We're going to go ahead and sketch ourselves a right triangle, an isosceles right triangle. So this is a right triangle. It's isosceles, meaning that both of these angles are 45 degrees. In this case, it said that the length of the hypotenuse they named as y. So if one of the legs is x, which means the other leg is x because it's an isosceles triangle, you would set up an equation as such and using Pythagorean theorem. So let me just show you why this works. You would have x squared plus x squared is equal to y squared. This is using Pythagorean theorem, right? A squared plus b squared is equal to c squared. In this case, our a and b are x, and our c would be equal to y because that's our hypotenuse. So if I were to simplify this further, combine like terms here, because these both have a coefficient of 1, you would get 2x squared is equal to y squared. Now, in order to isolate your y, let me rewrite this here. 2x squared is equal to y squared. Say I want to get y by itself. In order to do that, you're going to have to square root it, correct? So if you square root both sides, you're going to get y is equal to x square root of 2. Okay, square root of 2 is just a square root of 2. Square root of x squared is x. That comes on the outside, right? So I feel like even though I can't see your faces, a lot of you are probably freaking out right now because you don't get it and the radical is just intimidating you. I know you. I know how you are. So let me show you with some real numbers here so that you don't freak out as much and show you why this makes sense. So again, we have an isosceles right triangle, correct? I'm going to say that the legs of this isosceles right triangle is 3. If one side is 3, then this side is 3. And we're looking for the hypotenuse, which is always c, correct? So if I were to use Pythagorean theorem to solve here, you would have 3 squared plus 3 squared is equal to c squared. And we're looking for c. We're looking for our hypotenuse. So if I were to simplify further, this would be 9 plus 9 is equal to c squared, or taking it further, 18 is equal to c squared, right? If you square root both sides, you're going to get c is equal to the square root of 18, but you know that that can be simplified a little bit further, right? Let's take it up here. C is equal to the square root of 18, and c is equal to, if you were to simplify that further, that's 9 times 2, or 3 square root of 2. So the important thing about this lesson is that notice these two that we just broke down. Your hypotenuse, in this case C, or over here we found Y, which is our hypotenuse, your hypotenuse is always going to be equal to, let me do that a different color. Your hypotenuse is equal to the square root of 2 times the leg. Do you notice that? Your hypotenuse, in this case, was the leg, which was 3, times the square root of 2. So we're going to see that in this next lesson, dealing with this triangle, okay? This special type of triangle, this special 45, 45, 90 triangle. So theorem 8-5, which deals with this right isosceles triangle or 45, 45, 90 triangle, says that both legs are congruent and the length of the hypotenuse is square root of 2 times the length of a leg. Okay, so you need to remember this formula for this 45, 45, 90 triangle. Your hypotenuse is always going to be equal to the square root of 2 times whatever value your leg is, okay? And you'll see that notated in your diagram to the right. Your hypotenuse is always equal to the leg, which in this case is S, times the square root of 2, okay? And we'll see that in the following problem. So, say we take this into problem 1. Find the length of the hypotenuse. So, your hypotenuse, as per usual, is always opposite your 90-degree angle. This is an isosceles right triangle or 45, 45, 90 triangle, right? So we're looking for the hypotenuse. And according to the theorem above, we know that our hypotenuse is always going to be equal to the square root of 2 times one of the legs. But we don't have the hypotenuse here, which they named as H, but we do have one of the legs. So if we multiply the square root of 2 times the leg, which in this case is 9, you have your hypotenuse is equal to, and keep that 9 up front. Put it in front of the radical. So your hypotenuse here is 9 radical 2. Boom, you're done. We didn't have to use Pythagorean theorem. We didn't have to square anything. We didn't have to square root anything. We multiplied 9 times the square root of 2, which is simply 9 radical 2. That's your answer. Okay, it's pretty straightforward. Okay, how about problem B? So again here, we are still looking for our hypotenuse. Our hypotenuse in this case is x. So again, our hypotenuse is equal to the square root of 2 times the leg, correct? But we see here that our leg here is 2 radical 2. Now, before you freak out, I know that it's ugly, but it's doable. Let's do it. Our hypotenuse here is x equal to the square root of 2 times our leg. And according to this diagram, our leg is 2 radical 2. So, in our do now problem, I did put a problem as such, but I'm going to baby step this for you so that you don't freak out. I have x is equal to, now your whole number stays on the outside, so I'm going to keep the 2 here. But the 2 is being multiplied times radical 2 times radical 2. Okay? Baby steps. This is going to simplify to 2 times, square root of 2 times the square root of 2 is the square root of 4. Okay? The square root of 4, x is equal to 2. Square root of 4 is 2. So 2 times 2, x here would be equal to 4. I baby stepped it so that you guys don't freak out when you see the radical. Do not be intimidated by it. It's doable. So I want you guys to take a minute, if you like, pause the video. What is the length of the hypotenuse of a 45, 45, 90 triangle with leg length of 5 square root of 3? Okay, So take the minute, pause the video if you need to, attempt it, try it. Okay, so what is the length of the hypotenuse of a 45, 45, 90 triangle with a leg length of 5 radical 3? So you're looking for the hypotenuse here. And we know the hypotenuse of a 45, 45, 90 triangle is the square root of 2 times one of the legs, which we have here. We do not have the hypotenuse, but the hypotenuse in this case would be equal to the square root of 2 times the leg, and they told us that the leg here is 5 square root of 3. So 5 square root of 3 would be equal to, hypotenuse here would be equal to 5, which stays on the outside, square root of, and again, you can combine on the inside or multiply on this inside, square root of 6 would be your answer here. Leave it. It cannot be simplified any further. The square root of 6 is simply the square root of 6. It can't be simplified. It doesn't have any perfect squares in it, so just leave it. That would be your answer here. Okay? Doing okay so far? Okay, problem 2 is saying to find the length of a leg. So we're now looking for the hypotenuse anymore. You're looking for the length of a leg. So you need to have a little bit of experience with radicals. Again, I did post a do now problem that touched on this as well. So before you freak out by looking at this problem, take a minute to complete your do now, or make sure that you've had that done or have watched the video which I explained how to do this next problem if you come across it. So what is the value of x here? So x in this case is one of your legs, and they give you the hypotenuse here, right? Always opposite your 90-degree angle. They give you your hypotenuse here, and you know that that hypotenuse is always equal to the square root of 2 times one of the legs in this type of triangle, 45, 45, 90 triangle. Now, they're giving us the hypotenuse here, which is 6. So I would have this equation, 6 is equal to the square root of 2 times, now we don't know the leg, and they called it x. So you need to find x. So how do you do that? How do I isolate the variable? So here's what I have. 6 is equal to x times the square root of 2 is what I have right now. And you want to get x by itself. In order to do that, because the x is being multiplied to the radical 2, you're going to have to divide by that radical 2. Because in doing such, it cancels this out. So now I'm left with x is equal to 6 over radical 2. Now, if you watched the Do Now video and solved your problem, you know that it is against mathematical law to leave that radical in the denominator. You cannot. It is against the law. In order to get rid of that radical 2 in the denominator, you're going to have to rationalize it. It's called rationalizing the denominator. Multiply by radical 2 over radical 2. Because multiplying by radical 2 over radical 2, which is equal to 1, I haven't changed the problem. So I'm kind of manipulating this in such a way that I want to get that radical out of the denominator, but you can't physically change the problem. So in order to find that loophole around it, I'm multiplying it by 1, or radical 2 over radical 2, to get that radical out of the denominator. So watch what happens when we do that. So when I do that, you're going to multiply across, right? So you're going to have 6 square root of 2 over radical 2 times radical 2, which is radical 4. Okay? So now we have 6 radical 2 divided by, what is the square root of 4? 2. Correct? So, but we're not done. You can, in fact, simplify this a little bit further. Do not touch that 2 underneath the radical. It's underneath the radical. That means you're not allowed to touch it. But you can reduce whatever's outside of the radical. So this would be reduced down to 3 radical 2. This is equal to x. Okay? It's not that bad. All right, got it? So why don't you go ahead and take the time out to try on your own. If you like, you can pause the video, give yourself a minute. Okay, it says the length of the hypotenuse of a 45, 45, 90 triangle is 10. So they're giving you the hypotenuse. What is the length of a leg? So you're finding the leg here. But you already know that in the 45, 45, 90 triangle, your hypotenuse is equal to the square root of 2 times one of the legs, but we don't have the leg. What we do have is the hypotenuse. So the hypotenuse, they said, was 10, is equal to the square root of 2 times, we'll say, x, right? In order to isolate the x, you're going to divide by the square root of 2 on both sides, right? So that it cancels out here, and I'm left with x is equal to 10 over the square root of 2. But as we did in the previous example, you cannot leave that radical 2 in the denominator. So in order to rationalize it, you're going to multiply by radical 2 over radical 2, giving us 10 square root of 2 over 2, which is then simplified further down to 5 radical 2. This is equal to x, or one of our legs, we'll say. What do you think? Good? Okay, and then it says the reasoning in problem 2. Why can you multiply 6 radical 2 by radical 2 over 2? And we did discuss this already. It's because radical 2 over radical 2 is equal to 1. So multiplying by that radical 2 over 2, multiplying by radical 2 over radical 2 is not changing the problem. Is not changing 6 over radical 2. We're simply rationalizing it so that we no longer have the radical 2 in the denominator. Let me rephrase this. It's not changing the value of 6 over radical 2. Okay, we didn't do anything illegal. We didn't change the value of 6 over radical 2. We just manipulated the way that it looks so that it no longer has that radical in the denominator. Okay, so let's apply these past two examples to a real world application. And I think you might have had something like this on your math Excel last night. Okay, when you apply the 45, 45, 90 triangle theorem to a real life example, you can use a calculator. So if you haven't already, take out your handy dandy calculator so that we are not leaving this in radical form anymore. You're actually going to multiply it out and get a decimal value. So finding the distance. A high school softball diamond is, in fact, a square. The distance from base to base is 60 feet. So base to base, this is 60 feet. So you kind of have to evaluate, like, what are they talking about here? I'm going to say this is the home base. I'm going to say this is base 1, or we'll say first base. This is second base. This is third base. Okay? So it says the distance from base to base is 60 feet. To the nearest foot, how far does a catcher throw the ball from home plate to second base? So home plate is up here, second base is over here. So sometimes you kind of have to get a little visual in your head and kind of actually see what they're talking about by maybe sketching yourself a little something. Do you see it? Okay, so that diagonal in the square is your hypotenuse in this triangle. Do you see it? Okay, so being that this is a square, that means this side is equal to this side, and this is an isosceles right triangle, making this a 45, 45, 90 triangle. So you know that the distance from home to second base, home to second, is your hypotenuse, right? the distance of that would be considered your hypotenuse of this 45, 45, 90 triangle. Okay, so being that the diagonal is your hypotenuse, we're going to use our formula. Hypotenuse is equal to the square root of 2 times one of our legs. So our hypotenuse here is considered D. D is equal to the square root of 2 times a leg, and according to this diagram, our leg is 60 feet. Therefore, our distance is equal to 60 square root of 2, but they're asking you to not leave this in radical form because they want you to round to the nearest foot. So do not put 60 radical 2 feet. They want an approximation, meaning you have to punch this into your calculator and get a decimal form. If you in fact put 60 square root of 2 into your calculator and hit enter, it's going to give you a decimal value, an approximation. So because we're dealing with a real world problem, put it in an approximation that we're dealing with. We don't give length as 60 radical 2. We give it as an approximation or a decimal value, possibly. So your distance here would be approximately, this is the approximation symbol, approximately, I'm getting 84.85281374, something like that. You don't have to write all that down. They're asking for an approximation to the nearest foot. So you're going to look at this value. If it's above 5, you're going to round 84 up. If it's below 5, you're going to round or keep it the same. So your distance here is approximately 85 feet. Okay? Not that bad. So we're just taking the two problems that we previously did and applying it to a real world problem. So you guys are going to take the time to try your own. You try. If you like, you can pause the video and try it on your own. Take a minute here. Okay, it says, you plan to build a path along one diagonal of 100 by 100 foot square garden. To the nearest foot, how long will the path be? So, again, if you can't see it in your mind's eye, draw yourself a little something. Sketch yourself something so that you can visually see this image. So you have a square garden, right? Some little flowers everywhere. You have a little garden, and it's saying you're building a diagonal path through this garden. And it also tells you that this garden is 100 by 100 foot, making this isosceles and making the triangle that it consists of an isosceles triangle, or a 45, 45, 90 triangle. And we know that the formula for this, your hypotenuse is equal to the square root of 2 times one of the legs. And in this diagram, one of your legs is 100. So you should have hypotenuse is square root of 2 times 100, or h is equal to 100 square root of 2. When you punch this into your calculator, you should get an approximation of your path. You should get h is equal to 141.4213562, something like that. That's what I got. When you round that, you should get your path is equal to 141 feet. It's asking you to round to the nearest foot. So you take a look at this number here. Because it's below 5, you're just going to keep this number the same at 141. Okay, so that wraps up today's lesson. We're going to stop there today. Tomorrow we're going to pick up with problems 4 and 5 from the packet, which deals with another special case triangle, which we'll get into tomorrow. Again, if you guys have any questions, comments, or concerns about this lesson or having a hard time, I'm definitely here for you. You can send me an email or preferably a Google Hangout. If you have any questions, I can record a quick little video for you explaining things for you. Yeah, if you have any questions, reach out to me. I'm here. Otherwise, stay tuned for tomorrow's video. Have a good day, guys.